Good afternoon. The next lecture is by Pant. She is a principal engineer and academic research director at Intel, and she will tell us stuff about how they get into the 21st century, into the AI age.
Hopefully. Thank you. Thank you, Dr. Katz, and thank you, everyone. So I'm going to actually spend the first couple of minutes just talking about what I do. Let's see, and I will talk about Moore's law a little bit, because trying to understand what you all know about Moore's law, and I'll see if I can guide you on the right track with respect to Moore's law. And then what I'm going to do is essentially talk about a couple of emerging technologies which are probably very, very relevant given where we are today. So that's roughly. And I, even prior to that, just talk about how we do research at Intel, because I think research is something that is on everyone's mind here. So let's put that. I have my disclaimer slide as part of Intel. So I will get into this talking about Intel's research capabilities, but let me just spend a couple of minutes talking about myself. I am basically a circuit designer. When I picked up my PhD, I want to say I picked it up last year, but maybe a few years before that. I joined, at that point of time, it was the Alpha group of digital, which was already acquired by Compaq. And I joined the Alpha group, and they were working on Alpha, on the Alpha line of servers, for those of you who remember. And then about a year later, our group got bought by Intel. This is in 2001, actually. And so for the first 10 years or so, 10, 12 years of my career, I was working on the next generation of server microprocessors, basically looking at power delivery, circuit design, microarchitecture. To an extent, architecture. I did go down the stack a little bit into devices too. And then I moved on to something closer to my heart, into the research side. So I did develop product experience before I moved into the research wing. When I'm saying the research, Intel is a big company. Any idea on how many people work for Intel? It's more than 10.
30,000.
30,000? Higher. 50? Okay. We are about 100,000, 110,000. So it is a big company, and the reason I'm saying that is it is an ecosystem in itself. So you can actually really shift from quote unquote one career to another and still work under the umbrella of Intel, because it's such a big company. So I moved from working on products to the research wing, which was really very different from working in the product space. And if you talk about Intel's research capabilities, essentially there are two groups. One is a group that is attached to the manufacturing wing of Intel, which is called components research. So to think of working on the process side, lower down on the process side, enabling, looking at novel integration, looking at new devices, etc. So that's one side. And then there is Intel Labs, which is the upper part, where they enable novel capabilities. And together, the components research wing and the Intel Labs wing essentially cover the Intel research efforts for the corporation. We're about, I want to say about 1,000 or so people. So 100,000 people. We carry a lot of weight because we basically are sitting at the front end driving Intel's direction moving forward. But of course, we can't do this alone. And so right at the bottom, we have a wing called University Research, and that's the wing that I'm actually driving. I'm driving Intel's University Research, so more external facing, because we can't get things done alone. So we have to reach out and work with new minds, fresh outlook, fresh direction, reach out to the broader community in a collaborative fashion, clearly, because we are working with people like you, who will go on to either become academics themselves, or perhaps come along to join Intel subsequently, the next generation. So, and I'll spend a few minutes talking about what we do in Intel's research front, because I think that's something that you might want to understand. And then I'll I'll move on further into talking about emerging technologies. Yeah.
I know
Verse.
very little about hardware, but people tell me that Moore's law doesn't exist anymore.
Excellent segue into my next slide, which is Moore's law. Thank you. So let me start by actually asking you all, Moore's law, I'm assuming people have heard of Moore's law. So how many of you think Moore's law is about improving frequency and power by shrinking your transistors? And they're raising your hands. Okay, I see a couple of hands. Okay. How many of you think that the performance of a system increases by the square or doubles, whatever, every some amount of time if you increase the complexity? Raise your hands. I mean, that's what do the rest think Moore's law is? I don't see many hands going up. Any takers on what do you think? Does anybody have an idea of what is Moore's law? Yeah, go ahead.
The processing power will double every, I don't know, 1 or 2 years.
Some amount of time. Okay, you say the processing power will double at some cadence. Any other? Let me ask you, how many of you think Moore's law is dead? Okay, the more and more people thinking Moore's law is dead, maybe that's what's doubling every couple of years, right? All right, so let me tell you, Moore's law, and by the way, that is a reference to the paper, and if you haven't read it, I would encourage you to go and read what Moore's law essentially. It is basically talking about economics. It's all about cost. It's not about performance, it's not about power, it's not about frequency. It's really about cost. And this is a snapshot from that paper, which says with unit cost falling as the number of components per circuit increases. This was written many years ago, by 1975, economics. I've highlighted economics. It is essentially law of economics may dictate squeezing as many as some number of components on a single silicon chip. So essentially, it says that as you pack more and more functions onto a single chip, the cost per function is what decreases, right? Now, what someone said with respect to your frequency, your power, your complexity, etc., that's Robert Dennard scaling, if people have heard of, or Pollack's law, different aspects. Those are the ones which are essentially tottering on the edge or not surviving. But Moore's law is a law of economics. It's really a law of nature, from that standpoint. Is that clear? Right? So the question is, so what's been going on? So how have we been essentially pushing Moore's law forward for so many years so far? It's essentially CMOS scaling, right? That has been the key enabler for giving us the cost benefit, the economics benefit of Moore's law. And yes, scaling is how much you're limited by physics. How much can you scale, right? We announced our 10 nanometers. We are in the research phase of our 7 nanometers, and we're shrinking down. But moving on ahead, it's not just going to be CMOS scaling. There's more. Again, no pun intended, but there's more to Moore's law than just CMOS scaling there. Alongside with CMOS scaling, heterogeneous system integration, you have 2D integration, you have these SoCs, system on a chip, SoCs. Then you have 3D integration, where you have system in a package, where you start stacking up in the third dimension, where you bring in heterogeneous components into a system to give you the functionality that you're looking for and to give you the cost benefit that you're looking for. We announced FinFETs a few generations back, where instead of being in the 2 dimension for our devices, we have a third dimension on our gates. We're looking at further techniques in the process front and the design front, growing in the vertical direction primarily. Fitting that in, we're looking at novel architectures, novel data processing. Our data patterns are changing, and then obviously the changing, if you're changing from structured to unstructured, then you have to be able to interpret that data differently, and so you're looking at novel techniques. We're looking at novel functions that come up, the AI workloads that you all are familiar with, they're not like the traditional workloads that we have in the past, and so we have to look at, probably combining compute and memory together so that you can actually tackle those workloads, etc. So as long as all these things are still there, Moore's law is alive. Right? I mean, any questions? By the way, feel free to ask me any questions as you're going along. Yeah, go ahead. I may not have all the answers, but go ahead.
Yeah, I mean, as long as you don't have a new method to create gates, there is some limitation to the size that you can reduce the chip to.
Yeah.
Even if you stack them to 3D, and then you still have the same amount of material, even the cost will stay, I wouldn't say it won't go down, but not exponentially increase.
And that's the challenge, right? That's the continuous challenge that we all have to work towards. And so you keep finding, and again, for the last 15 years, I've been hearing Moore's law is dead every year. I mean, after a while, we keep.
It needs to exponentially increase.
So just hold on. So that's a good point. I think in my backup, let's see if I have it there. Okay, let me just hold that, because I think I should be able to address what you're saying there. So this is clear. Moore's law is really not, it is expectation of continued economic innovation. The other parts that you hear about performance, frequency, power, etc., are, look up Dennard's law, look up Pollack's rule or whatever else, and you'll find those components coming together. So I think in my backup, anyway, Moore's law is alive and relentless. And okay, so law of diminishing returns, yes, this is just a curve. You're familiar with that. You discover something new, it looks promising, you have an exponential point where it's looking great, and then it begins to taper off, right? That's law of diminishing returns, okay? So we've had many of these S-curves, or law of diminishing returns. If you look at the process side, on the design side, on the architecture side, software side, etc. You find something in the process side, FinFETs, etc. You can look at single-threaded computation, then you went to multi-threaded computation, you went to single-core, multi-core, etc. At every point you discover something, you have a phase where it's performing great, and then it begins to taper off, right? So we have a lot of these S-curves, and the question is, in addition to that, think about a law of accelerating returns, which I think is what Moore's law is. And what do I mean by that? In your space, you're an expert in your own individual field, and you discover your space where you have your S-curve. Your S-curve is where in the beginning, it's looking promising, then it's showing a lot of promise, you get a lot of returns, and then it diminishes off. But then there's another S-curve that comes into play, and then if you essentially go along that, you have an exponential increase, and that exponential increase, which is the law of accelerating returns, is basically representing Moore's law to you. With that.
Yes, but it doesn't seem like the next S-curve is here.
That's always the case, right? That's always the case. We keep discovering and discovering. So for the foreseeable future, we can continue for the foreseeable future. Because we're always finding the next S-curve. We've been saying that for a long time, but we'll keep finding the next S-curve. Make sense? All right, okay. So do I have everyone's assent here, agreeing that Moore's law is not dead? It's alive, it's relentless, and you'll hear about it for a long time. I think TSMC yesterday or day before, they did their, I don't know what they've said in the past, but they've announced that Moore's law, their interpretation of saying Moore's law is alive. So we're getting people to recognize that it's not dead. Okay. All right. Having said that, so these are different areas that we essentially look at. We do look at communication. We look at our systems. We look at security. We look at sense making. We look at novel integration. We definitely look at compute. And so I've actually highlighted that here because this is something that I'll be talking about a little more going forward, and all fueled by making sure that we continue to sustain Moore's law. Okay, so let me talk a little bit about the research segment. How does the model typically work? most of Intel is working on a product. Most of Intel is working on a product. But as I said, the research wing is sitting at the front end of this pipeline, feeding into our product development. Okay, so we have something called a workstream model. Right there on your left is the entire whatever we work on the research front, where compelling ideas are essentially generated and explored. And then, just like you find something promising, you have to prove that it works, so you develop a proof of concept. Not all of them turn from just papers into proof of concepts, or from patents to proof of concepts, but then there is a set that turns into that. But one thing which I've been having worked both on the product side and on the research side, one key difference that we get challenged with is that you have a single proof of concept. It comes back. You get a paper out, a publication out, it's working. But when you come to high volume manufacturing, right, it doesn't work. You can't afford to have a yield of 10% and 90% of your die not work when you're actually trying to push it out to the customer. So high volume manufacturing is a very key factor that comes into play when you're on the product side. And so that's a trade-off. We trade that off with perhaps something that's the best or the most promising, because if it doesn't work on every single device or every single product that goes out, then it's a non-starter, right? So that there's a difference between having a research hat on and actually having an execution hat on. Execution hat on is what the product needs. So that funnel becomes smaller and smaller. You have a proof of concept, but then you realize that when you put everything else into the picture, a lot of it has to be discarded, and then you go into what we call a transfer, where it transfers from the research wing into the product teams, right? So when you're talking of compelling ideas, how do we generate our compelling ideas? University collaboration is a big contributor to our compelling ideas. This is why we're constantly exploring what's outside, what is possible or not. In addition to that, there are a few other efforts. We have something we call a TSLP, Technology Strategic Long Range Plan, where on a regular cadence, essentially, we reach out to the Intel community to say, hey, what are some promising ideas that you think we should be looking at? So that's an opportunity for within Intel. Then there is another side where we call them our business units. The product side is called basically the business units, because they are the ones who basically bring in the dollars. From their strategic standpoint, what should be the emphasis areas? So that also feeds into the compelling idea pipeline. And then we also look at something called research velocity challenges. What are some things that we can do with a quick turnaround time? Because turnaround, you can't sit. I mean, unlike research where you say, yeah, N+1, one more year to graduate, one more year you go on. No, but we can't do that when you're in this mode. You have your regular cadence. What's going to come out next year? What's going to come out? So you have your roadmap, and to fit into that roadmap, velocity is a big component that we need to emphasize. All right. So these are the avenues for feeding in what's next into the pool. And obviously, all along we look at competition, because we are all trying to. It's a constant race, right? Whoever moves forward. So that's definitely there. Okay. So on the research front, what do we do? I said research. I'm talking of university research. What do we do? We obviously work with academics, and we have three different buckets. Where we look at one, focused problem solving. Okay, then the second tier, and when I'm going down this, it's increasing amount of investments that we put into it. So it's going to show. Basically, what I'm trying to emphasize is that there's a lot of investment that we put into university research here. Right, so we have focused problem solving, where we're working with individual PIs. We have something called centers, where we form a multidisciplinary community where we work on a particular area. And then we have huge, large-size centers where we solve industry-scale problems. Okay, so there are different levels of investment. They're here. And basically, this whole thing is driven by the Corporate Research Council, and that's the one that I essentially drive. The Corporate Research Council essentially has participants across the company. Remember, we said we're 100,000 company. We have key people, technologists from different areas, whether they're on the server front, whether they are in our AI PG group, AI product group, whether they are in our PC segment, whether they are in our communication segment. We have key people basically participating in Corporate Research Council, where they define what are the new areas that we should be looking at, right? Filling the technology pipeline with promising ideas, future talent. So we actually have 14 or 15 targeted areas, and these are not new. You look at research in the materials and patterning space. Look at research in the devices space. Look at research in the manufacturing space. Push for research in the software and security area, in the CAD area, in the architecture area, in the circuits area. Name a particular area of interest, and we have targeted teams. We call them strategic research sectors. We have targeted teams who are solely assigned with identifying what are the technical gaps in that area, what are some of the research ideas we should be pushing forth in that particular area. Just focus on that area. Just focus on that area. But you can't work in isolation. So talk to the other strategic research sectors. But each of these areas, we basically fund professors and our graduate PhD students on research that aligns with our technical gaps in that particular area. Right? Does that make sense? Right. And we keep adding, if it's market driven. I mean, for example, AI is of course, something it's emerging now loud and clear, and so we have a particular AI SRS. Similarly, I'll be talking a little bit about cryogenic, actually quantum computing, which is the cryogenic computing. And so we've basically started an SRS in that particular area. In addition to that, we have talent development, which basically looks at bringing in talent. That is their focus across the board. And then we have business development, which basically works with our business units to make sure that we are aligning with the strategic direction of our business units. Okay? So that is at the lowest level. At the lowest level, I'm saying lowest level as in we're working individually with different professors in different areas. One tier up is we form these, we call them, okay, we have something called TLAs, which are 3-letter acronyms, 3 or 4-letter acronyms too. We have tons of them, and so sometimes acronyms get reused. In this case, we have ISTCs, ICRIs, Intel, NSF, partnerships, etc., ISRAs, ISRAs, etc. Yeah, there'll be a quiz at the end, what each of these are. But Intel, for example, you have Intel Strategic Research Alliances, Intel Science Technology Centers, Intel Collaborative Research Institutes, etc. You have all these acronyms, but basically, there are centers that Intel launches, not with a single professor, but with multiple different universities, targeting, again, a given area. And here are some of the examples of some of the centers. And this is not a comprehensive list at all. And each of these efforts, they basically have a cycle. We launch them year 1, there's a year 2, it goes through an execution phase, and then finally it goes through a mature phase. And if it makes sense, it gets extended for another year or 2. So they're always forming, executing, evolving, as you go along, and that's across the board. And this is international, and it's not just limited to the US. We have international efforts too across the globe, right? And then you can, some of them are listed over here. In fact, we have one at MIT, which is Systems Approach to AI. There we have Mapping the Mind, which is in Princeton. We have a Continuous Edge Learning and Intelligence Center, which includes Harvard and UCI, I think, UC Irvine, and UT Austin participating. So again, multiple universities, and when I say multiple universities, multiple professors and their students basically participate in research. And by the way, in all these cases, the goals are set very clearly in the beginning, and what you're pushing forward. And the question is, have you overlooked something? Yes, possibly. And so it's a constant evolutionary process. We are dynamic, we form, and we change direction based on what we discover along the way. And then at the next tier, the top tier, there's an example here of, it's called JUMP, Joint University Microelectronics Program. This is SRC sponsored. SRC, I told you I keep spelling out these 3-letter acronyms. And SRC stands for Semiconductor Research Corporation, and you can look it up, www.src.org. But under the banner of SRC, Intel, IBM, there are about 12, 13 other companies have basically come together. It's a massive effort. It's a 5-year-long effort where 6 centers have been formed, and these 6 centers, huge. There are about, I think, 20 plus professors per center. And there are 6 centers. There are 4 vertical centers. One of them in the communication space called RF to terahertz communication, it's called Com Center. There's one on intelligent memories called CRISP. There is one on distributed computing called CONNEX. There is a 4th center on cognitive computing called CBRIC. And all these 4 centers, supporting them, there is just a fundamental center at the packaging device materials level called Ascent. And then there's one at the architectural and algorithmic level called ADA. These 6 centers, they have a director, the primary PI running these centers. They're listed there. And that, but again, the whole team has got about 20 plus PIs per center. So think about 120 professors, 120 plus professors. I think there are about 400 or 500 graduate students, PhD students working with respect to this. And Intel is, we are one of the companies that's involved from the other side working on these centers. You can see the magnitude of the investment that goes into what we do. Right? This was started again in 2018, and it's finishing actually 1.5 years through, and it will probably go for another 3.5 years. And then there is an opportunity for extension of the efforts around here. And if you just look up JUMP on the SRC website, you'll see some more details on this. And by the way, this particular one, because DARPA, we have government agencies sponsoring this, DARPA, NSF, NIST sponsoring this. This is primarily limited to the US. This is not international. This particular effort is limited to the US, right? Yeah, actually there are 500, I have the stats here, 521 students, 128 faculty working across the 6 centers over here, right? Okay, so in addition to, so we actually have a VC wing in Intel. So anything that is really promising, Intel actually helps out to explore a commercial angle through it. So we actually have the possibility of seed funding, helping with launching a startup and helping with an expansion. So we have a group which is basically Intel Capital that's really chartered with, if something is promising and you want to basically take off in a particular direction, then we are there to provide some initial funding to help you do that. Okay. Now, okay, so having said that, our data, you all probably know that we are in a phase of data explosion. Right? I think the projection is what, 160 zettabytes of data generation per day by 2025. What's zetta? Any 10 to the 21? 10 to the 21 bytes of data, that's the projection by 2025. Huge amount of data. So number one, the amount of data we're producing is exploding. Number two, the type of data, we're moving from a most structured, where you know what the pattern is of the data, to an unstructured format of the data, right? Which means that it's harder to process, it's harder to collect, it's harder to analyze, right? So given that this is happening, this is basically challenging us now to think about new optimizations, whether it is looking at new forms of data parallelism, new numeric formats, new ways of representing that data, rethinking data compression that's coming in, looking at real-time quality of service requirements, etc. Just rethinking the whole thing as we have it today because of where we're headed, right? So then the question comes up, as we are moving into an era where we are essentially trying to really push the envelope, and we're saying push the envelope, I think what is it that we are all driven by? It doesn't matter if you're researchers, doesn't matter if you're working on products, doesn't matter if you're basically in in the business of wanting to make money. We're all driven by, hey, how can we improve the common good, right? And what does that mean? How can we as technologists, whether it is in the financial world, in the manufacturing world, in the automated world, etc., wherever, is that how can we push the performance to levels that are hitherto unthinkable, not possible at all, right? If you're looking at precision medicine, if you're looking at weather prediction across that whole huge amount of data that's generated, but real quickly, if you're looking at developing emergency response systems, if you're looking at personalized education for the next generation, which are things that we are thinking about on a global scale, what does that require? It requires more than 1,000x improvement in computer efficiency given what we have today. It's not easy. We're not talking of 1x, we're not talking of doubling, we're talking of over 1,000x improvement in computer efficiency, right? So what does that mean? That means to say that what we're doing right now is not sufficient. So we have to think differently. We have to think differently about how we compute compared to what we do today, right? So what do we do today? It's conventional, basically. I mean, what we've been doing so far. What does that mean? You have your flow chart, you know what the procedure is, and then you just run it through the flow chart and you generate your answers, right? That's what conventional computing is. We've gone into deep learning, which is what we are doing today, where your procedures are generated through training, right? And then you have once you're done with your training, you have your procedures, and then you do your inference and your understanding, you know your answers, right? Now let's go look at, we have to still move on ahead. And an example of this would be, brain inspired, which is again something that you're looking at, where you have many possibilities, many directions that you can explore, and then you adapt your answer with some kind of reinforcement or depending upon the environment. And in another direction, and I'm going to talk a little bit about these two that are neuromorphic in computing. Another one is quantum. In quantum, you have your answers available to you. They're all superimposed right there. And then you select and measure the correct answer. Right? These new ways of thinking, they're not really intended to replace what you have today, but maybe to augment, because the application suite is different. Right? So the new methods will probably help us with the new set of applications that come in. But in addition to, it doesn't mean that conventional computing is going to go away just because you have quantum computing, or deep learning is going to go away because you have neuromorphic. They're all going to come together to really produce magic. So I think Arthur C. Clarke had said that when you have a sufficient set of technologies, they become indistinguishable from magic, and we are basically at that threshold. We're beginning to look at making magic right there. So how many of you are familiar with neuromorphic computing? Yeah, there's at least a couple of hands right there. Okay. So I'm going to play a little video, if I can, on what we are doing with respect to neuromorphic computing. Let's see if I can get this on.
In the future, I see a new class of chip, one inspired by the human brain, unlocking new possibilities and making the world smarter and more connected. To me, this is the next evolution in artificial intelligence. With neuromorphic computing, we'll redefine what's possible. Self-learning neuromorphic chips will transform education, facial recognition, manufacturing, emergency services, smart cities. It's already here.
Okay, so get that going. Move that back. All right, that's a little spiel that we've been pushing forward. So neuromorphic computing, and then some of you are already familiar with it, is essentially saying, hey, let's figure out how the brain computes, and let's see if we can emulate what the brain, how the brain does what it does into what we're producing in terms of technology. And of course, one of the most fascinating things which you've heard, all of heard, is that brain computes what it, or does what it does in just 20 watts. That's 20 watts or even less, which is, I mean, maybe we'll get there someday, but we're all trying our little bit to do, so what is it that basically fundamentally different from conventional computing, right? So here are a few things which, again, maybe some of you are, perhaps all of you are familiar with this, that, number one is fine-grained parallelism with massive fan out. How is it different from our conventional computers? First of all, you have your element of computing being, or the neuron is so much smaller than the entire brain. So it's really fine-grained, number one. And secondly, every neuron is connected to so many other neurons. So there's a massive fan out. As compared to in conventional computing, you have a clock. Clock is pretty much the only thing that really communicates across the chip. And as opposed to in this case, everything, the connections are pervasive. Every single neuron is connected to a large number of neurons, right? The third thing is scalability. Whether you're looking at a 200 neuron worm or a human brain, the basic element is still your axons and your synapse and your that whole thing has really not changed. And so there's that element of scalability that the brain has, which is something that our conventional computing does not yet seem to replicate. Then the next thing is event-driven computation with time, in the sense that time is really some kind of a variable here, right? In the conventional computing case, you have a clock. I'm talking of synchronous computing. You have a clock, and the faster you higher your frequency, the faster you finish your task and you get done, right? In the case of the brain, as you all probably know, is that an event can occur at time 1, and it's different if that same event occurred at a different point of time, right? The actual event physically may be the same, but the implication of it might be different because it has occurred at a different point of time. So there's a time dependent aspect to it, and these events are basically called spikes, and that's what basically neuromorphic computing is essentially pushing forth, is spike-driven computations over there. The third thing is that it's low precision, more stochastic in its approach. You haven't heard of a 64-bit floating point precision operation of the brain. They basically need maximum of 1 bit. And when computation is done, sometimes it's okay to skip a computation. So we have to have models that really absorbs that randomness of stochastic approach that the brain does. Today's conventional computing doesn't do that. You have something, you miss something, then you've lost your potential output because you haven't computed that output, right? So again, just talking of the differences between what we have today, and then the other thing is that it's adapting and self-modifying. The brain doesn't have a training process and then an inference process. The whole thing is essentially just adapts on the fly. It absorbs, it learns, and it just executes as you go along, right? Again, that's another thing that something for us to bear in mind. And then given that the brain is so fundamentally different from what we do in conventional computing, how can we take steps? And we are all looking at being able to take steps towards doing that shift and making our what we produce in technology closer to what the brain essentially does. And so neuromorphic computing chip that we've come out with is basically a first step in that direction. So we release something, it's called, I don't know if you've all heard of the Loihi self-learning, it's a mouthful, Loihi self-learning chip that we announced last year. Loihi, I believe is named after a volcano in Hawaii. It's emerged, it's supposed to be coming out, so I think that's the analogy over here. It's a memory and compute integrated into one chip here. There are 128 cores. We have 128K neurons, 128 million synapses. The learning capabilities happening on the chip itself. It's scalable from that standpoint. It's obviously complex neural network topologies in there, and they communicate asynchronously. The cores communicate asynchronously through these spikes. It is, again, each little core has its own, there's no master set of rules. Each little core has its own set of rules. And again, they operate with their own distributed set of rules, but they all communicate with each other. So we announced that last year. And then earlier this year, so then there have been various generations of Loihi which have come out. And I think earlier this year, I think last month, was it 2 months ago, we announced, okay, like that wasn't a mouthful. We announced Pohohiki Beach and Pohohiki Springs, which are 2 research neuromorphic systems They are basically capable of scaling from 64 to 768 low-heat chips with massive number, 8 million to 100 million neurons per system. You can read more about it. I won't go into the details. But here's what is exciting, which you might be interested in. I'll talk about the applications and come back to it. And again, the applications, again, whether it's sparse coding or pattern matching, complex system modeling, etc., the intent is that they are able to solve it more efficiently, right? So here's where this is of interest perhaps to you all, where essentially Intel has announced an Intel Neuromorphic Research Community. It's INRC, there's another acronym over there. But it's essentially encouraging you all to participate. If you want access to the platform, you can essentially get access to the platform. You can, if you send a mail to inrc_interest@intel.com, the idea is to advance the capabilities on the test chip. So if you want to run your algorithms, you want to try things out, you want to run potential applications to look at the programming models, sensors, actuators, etc., then all of you can get access to doing so. Again, get onto the INRC community, the Intel Neuromorphic Research Community, to do that, right? Okay, so that was with respect to, again, it's a sneak preview on the neuromorphic computing side. And let me shift gears and talk about the other part, which is essentially quantum computing. So quantum computing, it's taken me a while to understand this, and I'm still in the process of understanding this. It's in that quantum realm, and it's not quite yet descended down. But essentially, the idea is that problems which were intractable currently today, whether you're talking of constraint optimization or looking at the material properties, etc., things which are NP hard, which are today deemed pretty much impossible, quantum computing is supposed to be able to give you the capability of solving those kind of problems, right? So let me just introduce this idea to you. Are people familiar with quantum computing? Anybody familiar with quantum computing? You, okay. So perhaps if there are additional questions, maybe I can come to you, because I'm myself learning about this. But essentially, here's the thing. Think of a coin. You have a coin. You typically say heads or tails. That's in classical physics, right? You say heads or tails right here. Now imagine, instead of it being heads or tails, you're actually spinning the coin. So while it's spinning, while the coin is spinning, it can be heads and it can be tails. It's got heads and tails basically superimposed on the coin. And so that is the quantum aspect to either be. But when it stops, it's either heads or it's tails. It stops being in the quantum realm. So while it's spinning is when it's in the quantum realm, and you call it a qubit. Once it has stopped, it's either heads or tails, and it becomes a bit, right? So while it's spinning, there's the concept of superposition. It's got a 1 and a 0, a heads or a tail superposed on it while it's spinning. All right. So number 1 is superposition. Number 2 is entanglement. I think the closest example I can think about is atoms in a molecule. They work together. So when I'm saying entanglement, when you imagine 2 coins spinning instead of 1 coin, imagine 2 coins spinning. So in that scenario, they could both be representing heads. They could both be representing tails. One could be heads, one could be tails. So you could have 4 possibilities that it could represent while it's spinning. So in that state, when the 2 of them are spinning in an entangled format, in other words, there is some relationship between them, you can have these 2 to the n possibilities. In this case, 2 to the 2, 4 possibilities in this case. But if you have n of them, n coins spinning simultaneously, you can have 2 to the n possible states superposed at the same instance of time. And this is basically the concept behind quantum computing. So if you have 50 entangled qubits, 50 entangled, they're most states in a supercomputer. And if you have 300, they're saying most states, and then the atoms of the universe. And the question is, hey, what's the fuss all about? If it's going to be that easy. It's not that easy, and you know why? Because of fragility. What is fragility? They lose that entanglement very, very easily. That entanglement remains for fraction of the time, microsecond. We're trying to push that to a slightly longer time. They can remain entangled. Any noise, any disruption, an observation destroys the quantum state of the structure. So fragility, and to maintain, to ensure that they are entangled, ensures we have to go through all kinds of lengths. And today we operate in the cryo world, cryogenic, extreme cold in the Kelvin, millikelvin, literally right down there, so that they remain entangled for a very small fraction of time. And that's why it's not reality today. Does that make sense? Ask me any questions or ask the experts, because I think we have a couple of people. Yeah, go ahead.
What do you mean with observation on your slide?
Pardon?
What do you mean with observation?
If you want to read out your answer, whether it's heads or it's got all the states in there, but if you want to read out what is the actual answer, the entanglement goes away. When you observe the final result. So in a big scenario, you have imagine you have all the states there, and you want to direct it towards being one particular state. But when you want to read that out, you've lost the whole thing, and then you'll have to regenerate. So qubits have to be, in reality, it's not just 300 entangled qubits that will give you the 300 states. Because you can't observe quickly enough, you have to keep regenerating. So you need thousands and thousands of qubits to do that. Yeah, okay. So that's just conceptual. I mean, again, they're getting to be reality. Hopefully they will all see the light of day in a commercial environment soon. But there are many challenges that we are looking at. So when we're talking of applications here, and think of some of the applications, right? Today I'm trying to make my travel plans. You're trying to make your travel. We're trying to optimize everyone's travel plans, and it takes forever because so many of us are trying to do this. But if all the possibilities can be resolved simultaneously, you can imagine how easy it can become. So travel and logistics are one example of where you would imagine something like quantum computing being used. Precision medicine or pharmacology is another one, right, where you have so many different possibilities, but you're trying to zoom in. So again, just you may think of other examples. When cryptography, when there are encryptions that have not been solved to date because there are so many possibilities and you can't get to that. It's actually a big area that quantum computing is essentially beginning to show potential into. And of course, the weather data, you have so many different possibilities. How can you improve your forecasting based on all the data that you gather from every single place and trying to get that right? All of it, there's an aspect of you can't wait years for the answers. You want the answers to come around right away, and that's where the benefit or the promise of this emerges. Okay. We have, this is again Intel working with QTech research. There's a collaboration happening with the Netherlands. We're working on this. Again, from our standpoint, Intel is a technology company. On the components research side, remember we have our research wing there. On the component research side, we're looking at the lower side, whether it's the patterning, the atomic layer control, packaging, which is again a big thing. On the Intel lab side, we're looking at the upper end of the stack, the algorithms, the system architecture, control electronics, etc., and the qubit actual operation and control. We are working in partnership with the Netherlands team to do that. So it's not enough to just have the qubit. And the question is, you have to develop the entire system. When you're talking of the entire system, the qubits have to communicate with each other. You need control electronics for that. It's not just a single qubit. They don't work in isolation. Then one tier up is that you want your you have to have compilers, different compilers from what you have today, and then of course you have your applications and algorithms. So at every level we have different challenges. Right? So at the lowest level, where we're looking at the quantum chip, there's obviously looking at the device design, fabrication. There's of course assembly and packaging. There's the connectivity, topology, and the connectivity that's happening. Then you go one tier up. Actually, before I do that, this is coming to your question. There are two types of qubits today. Spin, I will not go into the details, but there are spin qubits and there are superconducting qubits. And then this is basically the emphasis here is on the superconducting qubit progress, where we've gone from just creating a resonator to a 6-qubit system to a 7-qubit array to a 17-qubit array to a Tangle Lake. And just hold that. We have a little small video where we talk about that, but that's where we are at right now. I think that's 46. I think that's 46 right now. Okay. At the control level, because you need to be able to communicate with it, come to it, and if you need at least 2 connections per qubit, it's hard to imagine how many connections you will require, right? It's not really scalable. Then you talk about multiplexing. Okay, I can use the same connections for multiple qubits, and the question is, does it function at the low temperatures that you want? There's a lot of challenges coming out of being able to get that effectively done. Can I increase the temperature from, say, 0.5 Kelvin to 1 Kelvin, and maybe I can do some more multiplexing. So at that control electronics level, we have that. Error correction, you will have errors. As you go through it, the error correction is a big challenge over there, and that's simply because the qubits, they're fragile. Remember, they're fragile. When there's noise, they lose their entanglement state, and then you might have an erroneous outcome. That's why, because of these challenges, the reason I'm mentioning it, this is why it's not a full-fledged reality today. We have to navigate through these challenges, but we are getting there one step at a time. Okay. At the compiler level, because some of your quantum computing operations, they have to work with adjacent qubits. They don't work in isolation there. So the compiler, compiler must be able to orchestrate the placement of these qubits and at the right time, because again, there's a time factor to it. They all have a limited timeline. So everything at that optimization and the execution has to happen during that limited timeline for every qubit. Otherwise, the qubit doesn't exist anymore. So arranging that maximum parallelism under your timing constraints, you need separate compilers to be able to do that. And then finally, your of course, in the application space, there is a whole aspect of developing algorithms that will implement your qubits there. We have a qubit simulator that has been released again out there, and it's something that again you all can have access to. There's an open source release of it for people who are working in this realm to explore it further, and you can look at qubit simulations there. It is for broader community exploration. That's something that you can look at. And yeah, this I did speak to this already, right? You have compelling applications. You look at algorithms there, and you want to develop real workloads for your systems, for the early systems that come out. And so you're likely. So where will it likely sit, right? You will imagine it being applied basically to HPC, high performance computing per se, right? It'll be it's not going to replace your conventional or whatever you have in your data center, but imagine it to be a co-processor sitting in your data center alongside it, right? So we have 50 qubits basically envisioned to be, if we are able to get to 50 qubits, we imagine that to be a learning test bed for a quantum system. By the way, it's very hard to get from 49 to 50 qubits. I mean, that's itself, every single step you go up, it becomes increasingly challenging to do. So even small problems will require hundreds and thousands of qubits to solve them, again, because of the short time frame that each one lasts. It's basically the fragility that comes into there. Okay, and so 1 million qubits, yes, that's a dream. We're not even close to being there, but that's why if we get to, we'll be able to do our dream problems. We should be able to solve by them. Let me show you a little video on this set. Let's see if I can get this.
I've been working on quantum computing for almost 20 years, and for many years it was basically a physics experiment. But now we're at a different stage where more and more excellent engineering is needed.
In reality, QTech here in the Netherlands, they are experts in all things quantum. It's a very natural partnership where we bring our fabrication expertise here, they bring their quantum expertise, and together we co-optimize or co-design for quantum computing. What I'm holding here is Tangle Lake. This is our 49 superconducting qubit quantum processor. And this is our first step towards a quantum computer.
A quantum computer will not look like a classical computer. This is a machine that's going to look like no other that we've built before. You can't just take the quantum processor chip and plug it into an already general quantum computing system. We have to really take a systems approach to quantum computing because we have to build the whole quantum computing system.
What we are trying to do is we are trying to fundamentally create a different type of computer and where we are using the properties of fundamental properties of quantum mechanics to make computers, where we are not only processing zeros and ones, we are using zeros and ones at the same time.
We're currently making a spin qubit device at our 300 millimeter factory in Hillsboro, Oregon, and we're shipping those devices here for analysis.
Spin qubits have several advantages. They're very compact. If we were to cram them together in a square millimeter, there will be space for 1 billion spin qubits. Also, their states are very long-lived compared to other qubit types. And finally, they are relatively robust in the sense that they can operate at ever so slightly higher temperatures than the lowest temperatures needed for some other qubit implementations.
Intel is really unique in the sense that it can integrate billions of transistors on a single chip. Now imagine that those transistors can all hold a qubit. That directly gives us the promise that we can scale up to millions or even beyond.
So there's really no better system than a quantum computer that we would use to understand sciences such as biology, such as chemistry, medicine, how to design drugs, how to treat for cancer. With quantum computing, we have a goal of changing the world, but changing the world takes time. We still think that we're about 10 years away from something that will affect your life or mine.
I think the principles of quantum computing are very, very solid. In this lab, we don't question quantum mechanics. We evidence quantum mechanics every day. For me, it's not a question of if one can process information with quantum mechanics. It's the challenge of integrating a complete system, which, let me emphasize, begins with a quantum chip, but includes a whole lot of non-quantum elements as well.
I was born at the tail end of the Apollo missions, at the tail end of the space race. And this feels like my generation's space race.
Yeah. All right, so that was a little bit on quantum. Let's see, and I think that's what I have. Let me just get to my last slide. Okay. Right. All right. So, in summary, as I said, university research collaborations is a very, very important component of really Intel's eventual product portfolio. We are essentially exploring the future, and we are defining the future. We're basically moving ahead, and so we put a lot of emphasis on that. Data is changing, as I mentioned, right? Data is changing, and we are having to look at rethinking our design, our architecture, to essentially do our part to tap into the data revolution over there. And so that requires us to essentially think differently across the entire stack, whether you're looking at the process, at the device level, at the circuit level, the microarchitecture, architecture level, systems, algorithmic level, at every level. And together, for the foreseeable future, Moore's law is going to be alive, and it's going to be relentless. So that's it. Thank you.